Hey everybody, welcome to this video. My name is still Miss Bowman, and today we are going to go through basically week by week what we learned in our stats course. The purpose of this assignment is that we are going to map out what important elements we covered each week through the course. My goal is that you can use this on your final exam. So when you get to your final exam and you're like, oh no, I don't know what to do here, my hope is that you'd be like, oh yeah, well, let me go back and see which units we did what work. And then you can look through your notes, you can look through the practice problems, you can look through your homeworks, you can look through your other exams, and you'll be able to look through this that we're creating today. So let's get to it. So first and foremost, we're just going to start out with our very first unit, which was unit 1. Now this unit, whether we said it or not, was all about what's known as central tendencies. So there are a couple of common central tendencies that we use within our area of study. So I'm going to lay out 3 of them. Now, these should sound familiar to you at this point. All of this video should sound familiar to you. But the first one that we're going to talk about is mode. Mode is the number that occurs the most frequently. So if you're going to forget what mode means, maybe in your own notes, you write in parentheses, maybe most. What I'm going to put is most frequent number. So which number occurs the most frequently in your lineup of numbers? So if you go back to your notes or go back to that first exam or your homework, you'll notice that I gave you several raw pieces of data, right? Just numbers. And I had you identify which one occurs the most frequently. Next, we have the mean. No, I'm sorry, excuse me. Next, we have the median. We'll save mean for last because that's the one that's the cool one. So the median, this number or this word literally means number, right? So we are wanting to know what the middlemost number is when the numbers are in order. The numbers have to be in order. If you don't put them in order, then you will have a harder time finding the median, what's in the middle, the centermost. So I'm going to write that, the middle most number. I'm going to make sure to put in order because a lot of times I see students say, oh, well, I know how to find it, but then they don't actually put the numbers in order. You have to put the numbers in order. That is crucial to being able to solve these types of problems. Alrighty, so lastly, we're going to talk about the mean. The big bad mean, right? This generally means average. So when we're talking about averages, when we're talking about the mean, what does that actually mean? What are we indicating? Well, we are going to add up all of the numbers, all of the raw data points, and we are going to divide them by the number of raw items there are. Before we get into the equation for that, I'm going to write down a couple pieces of information that we need to note along the way. And notice I put average in all caps like that. I did that as a stylistic choice for myself because that's what we're really talking about. I hear the word average far more frequently than I hear the word mean. If you're like, Miss Bowman, I don't want to write it in full caps, it looks ugly, don't do it. It's your notes. Do whatever works best. These are your notes. I'm just helping you to create them. Alrighty, so let's talk about a couple of definitions or a couple of parameters that we need to know. So first we have this lovely little symbol X bar, which is the sample mean. Now, if you've been through the course and you're watching this video, you know that when we first started this course, I just called it the mean. We didn't worry about the sample part, we just called it the mean. Well, now that you've been through the course, you might understand, oh, there are 2 types of means that we can have, but we started out with our sample mean. So when we say the word sample, or when we have notation that's familiar to us, we have what we are going to pick as the researcher. So if it's the sample mean, that means that I, the researcher, collected that data. Alrighty, so then we have what's called the sum of the xi's. This funny little e, that always means sum. This x right here is the values of our data points, right? So of the raw data that we were given. And so we get the sum. or so that means the sum, right? So that is, you add up all of the individual pieces and add them together and you get the sum. Alrighty, next we have n. N is the number of observations. If it confuses you to say observations, you can say participants, right? Now, observations is kind of a better way to look at that, but it's the number of how many pieces of data we have collected. And then finally, I want to note that X just by itself, that means raw scores. So here are all of our pieces. Here are all of our parameters. Now let's look at the equation. So we've got X bar minus the sum of the Xi's over N. We have all of those pieces right here. So we got our X bar, we have the sum, we have the number of observations, and I threw in raw scores, which I'll show you in just a moment. Alrighty, so this week during week 1, we took all of these pieces of information, and instead of, leaving it at, okay, now we have X bar, we have the mean, we took it a step further, right, as a class. Instead of just saying, oh, we have the mean, the day is done, we took a step forward and we were trying to solve for also variance and standard deviation. So I'm going to go ahead and write what that chart looks like. So hopefully you all remember that the chart had 3 main components. First, we have our Xi's. These are our individual raw scores right here. These would be the values, the individual values of these dots right here. That's why I have that there. Well, we would want to add all these together and divide them by n. We would want to use this equation right here, and we would get X bar, which is our sample mean. Well, in this second column, we take it a step forward. So over here, we're going to do X sub I, minus X bar. So what this is saying is that we are taking these individual data points. So this first dot here would be a raw score. We're going to subtract it from X bar, and we are going to get a piece of information right here. The second time we would use this raw score right here, this little one right there, that dude. Yeah. And then we'd subtract from X bar and we'd get this piece of data, and so on and so forth. Every single time you do this, this value that ends up right here, this is always 0, always. I like to put a smiley face in there just because there's the opportunity. We want that to be 0 every single time. If this number is not 0, that means mathematically you have an error and you need to go look and backtrack where you have the error. Alrighty, so the last part of the chart, what we'll do is we have X minus X bar squared. So all of these data points right here, for these 4 ones that we're playing with, we would want to square them and write the value right here. Now, I know I'm just doing dots. If you want an example of where I use actual numbers, please go back to the homeworks, your practice problems, that sort of, all those places. But all of these added up, let's say we have all of our items squared, and we add them up, that equals out to be our SS. That is our sums of squared. So this is the squared calculations for the differences between our raw scores and our mean. Alrighty, so I'm actually going to draw a little arrow over here, just so we can get back to left to right again. And now what I'm going to do is I'm going to say, okay, well, what can I do with the SS? Well, with the sum of squares, we can now calculate our variance. So we can take SS over N divided by N. So our sums of squares divided by the number of observations gives us our variance. Now remember the word variance. What does variance mean? Well, variance, think of the word vary, right? How much our numbers differentiate or vary from the mean, right? Well, knowing our variance is cool, but what's even cooler is our standard deviation. And you're like, well, Miss Bowman, at this point, I didn't know what standard deviation was back during week 1. That's great. Hopefully you do now. So standard deviations are the number of deviations away from the mean, okay? So in order to calculate that, we would do the square root of the variance equals standard deviation. Yay, that's what we were looking for. We found it. Now, what I want you to reflect on for a moment is that if you're watching this video and you've been through the course, standard deviation is a component that we have looked at since week 1. So whenever we talk about, is this exam going to be comprehensive or not? Well, inherently, yeah, because we started with standard deviation and you will need standard deviation on the finals. So this course really is a building block course. All right, so that's really it for Unit 1. I hope that that makes sense to you. I hope that that's very appeasing to you. This is what we did. Hooray, let's move on. So now we're going to look at Unit 2. All righty. Well, Unit 2 was really whenever we started getting into transforming scores, as what Canvas says. But I'm going to write z-scores first. Then I'm going to put transforming scores in parentheses. So, have you ever been in a class where the professor says, hey, I'm going to give everybody a curve. Everybody's going to get a curve on the grade. And then they just gave everybody 5 points, right? That's not a curve. That's actual constant shift, right? We're not looking for constant shifts when we're looking at z-scores. We are talking about keeping the same distribution pattern or the same style of the distribution without a constant shift. And you're like, Ms. Bowman, what does that even mean? Well, that's just to give you some context that z-scores, it's like a measuring stick. So we want to take our original scores and we want to reform them. We want to reshape them. We want to mold them to be in a different form. Hence why we say transform scores. All righty, well, I'm going to do what I always do. And I'm first going to write the pieces of information that we need. So we're going to need X by itself. And if you'll remember, X equals raw scores. We did just write that up here. So if you don't want to write it again, you don't have to, but I'm writing it again. Alrighty, then we have this funny little symbol, sigma. Ooh, right? Sigma, remember when we introduced this, right? This funny little O? Well, this is what we need to call standard deviation from now on. Now we're changing our style just a little bit, right? So we calculated standard deviation up here. Well, now we're using sigma, and I'll show you why in a moment. But we also have something new to the mix, and this is mu. This funny U looking M thing, right? So this is actually our population mean. Now, during week 2, I said, hey, don't worry about the difference between mu and X bar. We'll get to it. Well, if you're at the end of this course, then you've got to it. X bar is our sample mean and mu is our population mean. Remember that if it's sample, that means we collected that data, right? We, the researchers, were able to find that data. Whereas if it's a Greek symbol, that means that we're making a estimate about the population, right? We're looking at the population scores. And remember, it's very, very, very difficult to get the population score for anything, right? You know, I could ask all Tarleton students a question, but the reality of me asking all Tarleton students a question is very low because there's a lot of students, right? Okay, so now what we're going to do is I just decided to make a fun arrow. That just looks like a fun arrow to me. You can make this whatever you want. But basically, I'm going to write the z-score formula for you. So z equals x minus mu over sigma. This is the one that you're familiar with, right? X minus mu over sigma. These are all the pieces that we need. Well, what I didn't tell you during this week was that we can write this formula a couple of different ways, and some of you were able to pull that together and figure it out because it makes your life quite a bit easier. So let's go ahead and go over those. So we have z. Well, what happens if we're looking for sigma? Let's say we have our z-score and our x and our mu, but we don't have sigma. Well, we can write this formula a different way, and it'd be like this. Sigma equals x minus mu over z. It's the same equation, same formula, but we've switched around some of the players so that we could have what we're looking for on the outside of our equation. Well, what happens if we're wanting to look for x, right? Let's say we are not given x, but we're given sigma, mu, and z. That equation would look like this. X equals sigma times z plus mu. I always remember this one because it looks like Oz, right? OZ, the Oz plus mu, Oz plus mu, right? Very cool. So now we could just solve to find x by plugging in the information we already have. And then finally, let's say that we're looking for mu. Well, that would actually be negative sigma times Z plus X. Now this one you could write a couple of different ways. So if you have it written a little different, don't stress, it should work. It should work itself out. As the main part is that you have that negative in there. Alrighty, so this is week 2. What we did was I gave you a series of Z-scores, or actually I gave you a series of raw scores, right? So 6, I don't know, just some random numbers. And I asked you to calculate Z-scores. I asked you to find what that would look like. So when we're talking about Z-scores, we're really talking about like a measurement tool, think of a yardstick, right? So if we're talking about yardsticks versus rulers versus tape measures, those all are different tools to measure the same amount of distance. A Z-score is another tool to look at distributions of scores. So real quick, I'm gonna throw in a distribution. So suppose we have a distribution that looks like this. Beautiful. Oh, wow, I actually drew that very well. This is what's called the normal distribution. The scores are normally distributed. So basically the biggest part is that it is symmetrical on both sides. So what we'd have in the middle is mu. That is the mean. That makes sense. And then what we would have is we would have our standard deviation. So 1, 1, 2, 2. And we know that most of the people, their scores occur in the middle of this distribution. In fact, 68% of people. So right here in the middle. That is where most of the scores lie in our normal distribution. And then we got 14 that live here. And then we got 2 that live here, right, in each one of those. So the reason I'm showing this to you is because in our class, if we didn't have enough time to fully cover this, what I want you to note is that now that you've been through the course, now that you understand what p-values are, we're wanting p-values that are in the very little bitty tails, right? So how this relates to z-scores is that this whole time we've been working with finding these score values, and we want to find things that occur in the tails. Well, z-scores help us to determine how far away our scores are from the centermost point, right? If you want to know more about this or about the visuals of normal distributions, let me know, or this is something that is commonly known on Google or in your textbook. Actually, this is also in your textbook. Look there too. But anyways, we're going to move forward now, and we're going to cover Unit 3. Now, Unit 3 was really where we got into the normal distribution. Remember this little guy that we just looked at? This guy, right? This is what the normal distribution looks like. So I'm going to actually leave that right about here. And then I'll do our notes. All righty. So Unit 3. The normal distribution. You're like, Miss Bowman, why didn't you just draw the chart where you're writing normal distribution? Well, you'll see why in just a moment. Alrighty, we also talked about proportion a lot this week. We said what proportion of the curve would be covered if somebody scored this or this compared to their peers, right? So let's take a moment to talk about, like, let's say this is your final exam. And let's say the mean is 50, right? So everyone in our course averaged out to have a mean of 50. Well, that's a really low mu, right? That's a really low grade. That means the majority of people got around a 50. As your professor, I'm very concerned, actually. I'm really hoping that the mean is much higher than that. But I'm wanting to know how many people scored a 50 or less. What proportion of the scores or of the students scored 50 or less? So we could apply these questions to our class with the normal distribution. Alrighty. Well, in order to find this proportion with our distribution, the first step will be to what? It will be to perform a z-score. So we're going to have z of x minus mu over sigma, which gives us a z-score. This was the week, y'all, where we first started using the calculator. So we're going to take the z-score and we're going to do step 2, which is we're going to put it into the calculator. If you remember, it's the very first calculator. Please go look on Canvas to be able to find the link. but we use this calculator. Now our third step, so we got step 1 is solving for Z. Step 2 is putting it into the calculator. Step 3 would be writing it out. So we have the probability or the proportion that Z is greater, this could be greater or less than depending on the problem, but bear with me, of Z, which we calculated and would put there, equals blank. Now this was where I had you, this was your final answer, whatever the calculator gave you, right? Remember, we said that if it was small, medium, large, right? But basically, I'm going to give you an example here. Let's say that the calculator printed out 0.45. Well, what we did during this week is I said, hey, y'all, if you want to, go ahead and move the decimal back twice, and that gives you 45%. So when we're looking at our distribution of scores, we have 45%. 45% of the curve would be about here, almost half of the curve. So if I'm looking for the proportion of students that made, you know, a 50 or less or whatever grade, 45% of them made lower than whatever score I'm looking for. Now, no, that wasn't the best example in the world, but hopefully that makes sense logically, the flow of logic. So on this, during this week, I told you that I didn't want this to be your answer, that this is your answer, but I wanted you to understand that we're talking about percentage. So if we're looking at the curve as a whole, we got 45% of the curve. Alrighty, well, hopefully I've beaten that into the ground enough. Let's move forward. So that was unit 3. That was pretty straightforward, right? We would just solve for the z-score, which we learned how to do already, plug into the calculator, and then we would have our output that we would interpret to be what proportion of the curve is covered. Well, now let's get into unit 4, which was the distribution of sample means. Keep in mind that whenever I say distribution, this just means how the scores end up laying out in the distribution, right? So where your mu is, you would expect to have the greatest point. That would be the highest point, right? Because you have the most people that are with the mean. And then it levels out as you get farther away from the mean, being that fewer and fewer and fewer people have those scores. All right, but what I really want you to note here is that this week we took it from single scores to sample means, right? So up here during unit 3, we just had one score. We had one value. Now what we did during this week is our first step is we had single scores versus sample mean. How I'm going to write this is how we did it this week, because we had part A and we had part B. Part A was all about a single score. Part B was all about a sample mean. So like we did in unit 3, single score is Z equals X minus mu over sigma. Cool. Whereas sample mean, the formula is a little different now. We have Z equals X minus mu over sigma divided by the square root of n. Now we have added this right here. So it's pretty much the same equation, except for we've replaced X with X bar, and we have added the square root of n. Well, this logically makes sense, right? Because for our single score, sigma divided by n would be 1, right? Because we have one score. Whereas now for our sample mean, we have several scores that we have to take into consideration, hence why we have the square root of n. So now I'm going to write part number 2, which is from both of these, we got a Z value. I'm going to use a different color marker because why not? So we got a Z value that we're going to plug into the calculator. This is the same calculator that we used the week before. Same calculator. For both of these Z values, we put them into the calculator, right? Now, what I'm not including in these notes here is what changes up in the calculator. I want you to make sure you understand that, so that's up to you. So please go play around with the calculator, make sure you know what you're doing. But then we plug into the calculator. Well, luckily enough, the calculator is awesome. So now for part 3, or step 3, we have P of Z. And I keep writing greater than. Remember that this depends on the problem. Here, you're going to write your Z-score value that you solved for. Close parentheses equals whatever the calculator has output for you. Boom. So this week where I asked you to stop at was similar to the week before, right? We stopped at whatever the calculator gave us. We use that output to talk about the proportion under the curve that is covered by this specific Z-score. Awesome. Alrighty. Hopefully all of that makes sense because we're going to go ahead and move on to talking about that first exam. So remember, exam 1 covers units 1 through 4. Please make sure that if you have questions about this, you look through your notes, you let me know, you go look at your textbook, you see what you made on that first exam and see if you like the grade that you liked or liked the grade that you got. If you don't like the grade that you got, you might want to rework those problems to prepare for the final. But alrighty, so units 3 and 4, I think we covered pretty well. Now we're going to move on to what's known as hypothesis testing. So we came back after that second exam and we were moving on into the next phase. Now, hopefully we're at the point where hypothesis testing makes sense. But back during this time period, I told y'all that I didn't expect you to get hypothesis testing during that 1 week, that this is something that requires time and effort and energy to understand, right? So I hope that by now we've all gotten it. But during this week, I told y'all to please not stress. Whether you listen to me or not is on you. But before I start writing anything, I want you to remember that I made a video and I posted it to Canvas. It's called the Hypothesis Testing Map. And I want you to go either rewatch that video or if you've already watched it, please pull out the chart that we made together. It looks like this. This is the chart, right? I walked you through how to build this chart and what all of the pieces mean. Please go back and make sure that you understand that video. What I'm going to put here is a very shorthanded and quick version of that. So let's get to it. All right. So unit 5, hypothesis testing. I'm going to write hype. That is short for hypothesis testing. Hype sounds fun to me. I don't know. What's all the hype about, right? All righty. So the first thing you have to do in hypothesis testing is you have to identify your null and your alternative hypotheses. Your null always means that there's no difference, 0. There is 0 difference. The null always means that there is no effect. Now we have the other one, which is the alternative hypothesis. Now I'm going to go ahead and make myself a little note down here to consider direction with your hypothesis, with your alternative hypothesis. All right, so let's go make a cute little chart of what this means. All right, so first we have our null, which means there is no difference between two means, between the mean, the population of the sample, right? Your treatment had no effect. That is the hypothesis. Well, in order to, claim that this hypothesis is the one, you would want a p that is greater than 0.05. This would mean that the data are plausible and you would fail to reject. FTR is shorthand for fail to reject. You would fail to reject the null hypothesis and you would conclude that there is no difference between. That is the flow of hypothesis testing. Whereas for H1, we would try to say that yes, there is a difference between my sample and my population. There's a difference between pre-test and post-test. My experiment had an effect. So we would need evidence of p is less than 0.05. What we would be able to say is that our data are rare, right? And we would reject the null. Now, I'm not writing those words out in this video. You write them out if you want to, but I'm trying to keep this video as short as possible. So then what we would conclude is that, yes, there was an effect of the treatment. There was an effect of pre-test, post-test. There was an effect of whatever thing that you did that you were investigating in your research study. So with this being said, I want y'all to remember that now that we've talked about Bayes land, Bayes is different than hypothesis testing, but this right here, this is the decision. These two are the decision, right? Well, this one's decision and that one's the conclusion. So decision is rejecting or failing to reject. I'm going to write decision. Because a lot of people are like, what do you mean make a decision? Well, your decision is either you're going to reject or fail to reject. And then you're going to have a conclusion. In your exam or on your exam, I expect that you will write out what this means. You will write out due to P being greater than 0.05, we fail to reject the null and we conclude that there is no effect of whatever thing that you have, right? Whatever thing that you're studying. Alrighty, so I'm going to make a note down here to watch hype testing map video. If you'd like to watch that again or watch it for the first time, if you have not seen this video yet, go watch it. And I'm also going to say, look at chart. That's the one that I just pulled out the video out of the binder. Make sure that you go look at your chart so that you can follow it. That's all you got to do is you got to find your p-value and then determine which side it's on and then follow it. I mean, hello, it's awesome and great. Miss Bowman made it. Use it. Alrighty, that was the first part of Unit 5. Now, the second part of Unit 5 was confidence intervals. So note we're at Unit 5. This means we're, halfway through the units because there are only 10 units. So this was when we got started on confidence intervals. So hopefully at this point you all know the equations for confidence intervals, but I'm going to go ahead and write it. So 95% confidence interval equals X bar minus 1.96 times sigma over the square root of n. The other boundary would be X bar plus 1.96 times sigma over the square root of n. Alrighty, that would be the long-handed way to write this. I'm going to write or X bar plus or minus 1.96 times sigma over the square root of n. This plus or minus indicates that you would want to do plus and minus, right? Now, where I found a lot of students messing up was at the very basics of how to perform the equation for this. So I'm going to make a little note. So the first thing you'd want to do to solve on any of these, but I'm going to write on the second one, is you'd first want to solve this part. PEMDAS, mathematically, that one comes first. You want to do that primarily. So once you get your sigma over the square root of n, then you can solve this piece of information times 1.96. I'm going to write second there. And then finally, what you'd want to do is X bar plus or minus the value that you get for these two. Plus and minus, right? So you'd end up with a lower and upper limit of the confidence interval. So you'd end up with a lower amount and a higher amount. And you would expect that your mean is in between those two, right? We're predicting. So we would denote that as we are 95% confident that mu, oh, I didn't write mu fancy. Oh, well, you know what it means. Mu, that's it in words, is between this and this. What I want you to do is on your exam, you need to write this. You need to write the statement. It doesn't really make sense without the statement. I want the statement. And what I want is I want the lower amount to be here and the upper amount to be there. Because it makes sense, right? You do the lower amount first and you do the upper amount second. There are several students who write it the other way and I'm like, oh my gosh. So please try to write it this way. Alrighty, so I'm gonna make us a note down at the bottom of this. Because now, when we first learned this, I just told you to use 1.96 and move on, right? So that is for, that 1.96 is for a normal distribution. That is for a normal distribution. Now, you know that when we get into a t-score or a t-test, we use a different value. But if you read the word normal, normally distributed has a distribution that is normal, blah, 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 whatever, that means you'll want to use 1.96. All right. Well, now that you understand, so this is really the last step that we need for the normal distribution. Because the next week, the next unit, we switched over to unit 6 being all about t-tests. Yay, we're finally getting into t-tests. T-test means that you're comparing, right? We are comparing this to that. This is really the first week where we got into stats world, right? Z-scores are cool, but this is really where we need to be, over here in t-tests. This is what we've been building up towards. All right, so in a t-test, I'm gonna start out by writing out the parameters. So again, we have X bar. Wow. At this point, if you don't know that X bar is sample mean, I would encourage you to learn it because X bar is sample mean. N is the number of participants. Can't write anymore. It's fine, just halfway through the video. And then mu is the population mean. All right, these are the pieces of information. Wow, my handwriting got real bad real quick. Sorry, y'all. Anyways, so now we're going to be talking about what a t-test is. Well, a t-test is a t-distribution. Now we've switched distributions. We went from a normal distribution to a t-distribution. If you want to know what that looks like, I'd encourage you to look in your book, or I would encourage you to look online. But basically, in order to solve a t-test, we are going to need the following equation. So we got t equals X bar minus mu over sigma hat divided by the square root of n. This looks very familiar. This looks like the z-score formula, right? We got X bar minus mu over sigma hat divided by the square root of n, right? Let's go back and let's look at our z-score formula, right? So this one for sample mean, we have X bar minus mu, a sigma hat over a square root, or sorry, just sigma. Well, I just gave it away that the big difference is that sigma here is what we're told. We're told that the standard deviation is this. Whenever we get over into t-test, we have to estimate what that sigma is, hence what the little hat is for. The hat denotes that we need to have an estimate. Well, in order to have an estimate for that, we use the following equation. SS over n minus 1. So the square root of SS over n minus 1 is sigma hat. So what we do is we plug that in here. We take our number of participants, we take our sample mean, and we take our population mean. Again, it's the same game as we've been doing this whole time. We're taking pieces of information and plugging it into the bigger, broader scope. We're plugging it into that main equation there. Well, once we get our t value, right, once we have, I'll use a different colored marker. Once we have t, we would take that t and we would plug it into the calculator like we've been doing all along. What I want to note is that we've reached the point where that t value you need to pay attention to, because instead of hitting a normal distribution, you'd want to go to a t distribution. That's one of that first options on the calculator. Please make sure to pay attention to that. And what that would output is a p value. All righty, well, remember last week when units in confidence intervals, we really started getting into hypothesis testing, right? Remember? And we said that we wanted that p value to be less than 0.05 if we're going to reject it. So if you get to the calculator and you have a p value, you come back to your chart and you say, which one is it? Oh, it's this one. Cool, that means it's plausible, we fail to reject, etc. You come back to the one that it matches. I want to take a quick moment to note something here. This is really where we started having the funny E. Let me show you what the funny E looks like. So let's say we have a P, let's say we have an output of 1.16 E to the negative fifth. That's kind of scary looking. That E throws a lot of people off. My favorite is people are like, oh, that means blah, blah. Like I love reading different people's interpretation of it. But basically what you do in this situation is you take the E, right? You say, that's an E. And you look at the number and you say, okay, negative, okay, okay. What this is saying is that this decimal place needs to be moved 5 times. So 1, 2, 3, 4, 5. That is the new location for our decimal place. So I'm going to go back in and fill it in with all the zeros, because each one of these arches, right, is a 0. So this is 0.00016116116. I don't know about y'all, but that is definitely less than P of 0.5. Like this number is definitely less than 5, right? 0.05, definitely less. So thus we would reject the null. We would have rare data, right? Because it's very small. The smaller, the better, right? The more rare. I know that's hard for us Texans because bigger means better in Texas, but you know, not always, not in p-value land. So yeah, that's the t-test. What we did was we used the t formula, which we should make sense because we started with the z formula. We plugged into the calculator and we had an output. Now let's move on to unit 7. We're almost there, guys. We really are. All right. So in unit 7, we switched gears and we started working with what happens if we have 2 groups of participants. So in unit 6, we had 1 group. Now we're going to look at what it means to have 2 groups. So this is independent. I'm going to write indep for 2 samples t-test. The independent samples t-test will always be 2 groups that are independent of each other. What that means is that, like, let's say we separated our data into male and female. For the way that we're looking at this, you're not going to be both male and female. You're going to be one or the other, male or female. You could do this in a lot of different ways, but basically yes and no, 2 different groups. So hence independent sample t-test. They're 2 independent groups of each other that we want to compare. So let's say in group 1, and then we have group 2. Well, in group 1 and group 2, we need to have the same pieces of information, right? So we're going to start off with n. If you remember, n is the number of participants. And this little 1 and this little 2 here, that's just how I'm noting group 1's value of n, group 2's value of n. Well, what I like to go ahead and do here is I also like to add in the DF, the degrees of freedom, because this is really where we start to see degrees of freedom. Degrees of freedom, remember, I'll just make a little note here, df equals n minus 1. This is really where degrees of freedom started in our course. Basically, we're taking n and we're subtracting 1 from it. Now, philosophically, if you want to understand why we remove 1 to have the degrees of freedom, I would encourage you to think more about that, read more about that. Ask me about that, that's fine. But that's really something that you'll get into your master's level later on. For now, you just need to know that degrees of freedom is n minus 1. All right, we will also have x bar 1 and x bar 2. So our sample mean for group 1 and our sample mean for group 2. And then our sums of squares 1 and our sums of squares 2. Now note that the common theme of this entire course is that I give you pieces of information, but there's not this one. Well, chances are you need to solve for that one, but I will always give you the tools to be able to solve, regardless of what pieces you have. The goal is to solve the puzzle or to solve the problem, right? That's why I like math so much, is because it's a bunch of like problem solving, right? You use this bit and then you transform it and then you have something else. So please note that I won't ever leave you in a situation where you don't have what you need. Alrighty. So for this, we are going to use the t-score formula because we're running a t-test, right? Well, remember the t-score formula that we looked at Unit 6 is going to be different than the one that we used in Unit 7. So it's going to look like this. So the formula that we're going to use, so first we're going to solve. And the first formula we need is the t-score. So x bar 1 minus x bar 2 equals mu 1 minus mu 2 over sigma hat pooled times 1 over n1 plus 1 over n2. Okay, well, based on this chart, we have all the pieces of information we need. So we have x bar 1 and x bar 2, we have our n's, but we don't have the sigma hat pooled little notion, and we don't have any mu's. Well, I'm going to go ahead and give you a hint that this right here will always, in this class, for our scenarios, be 0. I'm gonna make a little smiley face. That is 0. Because remember, with hypothesis testing, we are assuming that the difference between mu1 and mu2 is 0. We have a bias, well, not even a bias. To avoid bias for the alternative, we stick with the assumption that mu1 and mu2 are not different. They have 0 difference. So this will be 0. Cool. Well, now we have all the pieces except for the sigma hat pooled. So let's talk about sigma hat pooled. The equation for sigma hat pooled looks like this. The square root of SS1 plus SS2 over DF1 plus DF2. So what this means is, well, we already have our degrees of freedom and we have our SS's, thus we can solve for sigma hat pooled. Where students mess up the most in this type of problem is they say, great, I have the denominator, boom. And they leave out this part right here, the square root of n1, 1 over n1 plus 1 over n2. They leave this part out and they assume that this is all of the denominator. I want you to make a note to yourself of how you are going to remember that, right? So for me, I'm going to do something like this. I'm going to underline this. I'm going to circle this. I'm going to draw an arrow. And then for me, I'm just going to put a big old like parenthesis right there. Don't forget that. Do not forget this part right here. A lot of students did this. So then their t-score was wrong. So they put into the calculator wrong, and then their printout was wrong. Now, note for that, I do give you partial credit, but this is a pretty big thing to forget about. That's a pretty big piece of the puzzle that you don't want to leave behind. So anyways, so from all of this, we are going to get our, oh, I need a different color marker now. I'll just use this one. Okay. From all of this, we're going to get our t-score. Yay. So I want to make a side note here that you need to consider direction. So I'm going to put 1.5 as a step. Consider the direction of your hypothesis or the direction of your study, right? Greater than, less than, increase, decrease. Because remember that if it has a direction, you're going to do one direction. If it has two directions, you're going to do two directions. If it's in the middle, right? So make sure you take some time to consider that there. But step 2 will be to put it into the calculator. Remember that you're still going to want to consider your t-value, right? You're still going to want to think at the top of your chart what, you know, what setting you want it to have. Make sure you set it to t distribution and not normal distribution. But then what you're going to do is you're going to put it in the calculator. And then step 3 is you're going to have your P of t. So the probability or the proportion that t is greater than whatever your t-value was, right? Whatever you calculated equals blank. Whatever that looks like, whatever that printout is, that goes there. I'm going to put a note that this is where you want to use hypothesis testing. But that's where you're going to want to say, okay, I got P greater than 0.05. Then you'll run through the steps of your chart. Awesome. Hopefully that makes sense. Then you'll want to go through and write your really good conclusion. Please make sure on each of your problems that you're writing the conclusion, you're writing what this means to the bigger picture. That is an important grade. It says it in the instructions to do it. I haven't included it on our little notes here for the sake of time, but make sure that you are doing that. Alrighty, so now let's talk about Unit 8. Well, Unit 8, we moved back into what we know as confidence intervals for t-tests. So same principles before with confidence intervals, but now we're going to look at it from a t distribution point of view. So I'm going to get started. So we have 95% confidence intervals that x bar plus or minus t star df times se. So now we've introduced this idea of t star df and se. All right, let's do t star df first. So, and you can do this in either order. You can do standard error first. I really don't care. Whatever order you want to do. I just start with t star df because I think it's the simplest. So t star df equals, or remember, that you need to have n minus 1. So you'll need to know your number of value or number of participants, right? And then what you'll do is you'll go to the calculator and you'll plug it all in the calculator. If you don't remember how to plug it in the calculator, what do? Well, you go to your notes and you look at what you did before. You look at the most previous exam. You look at our notes from class. You look at your homeworks. You think about it, right? And this output will give us from the calculator the T star DF. Make sure that you remember how to do that. I know I'm confident in all of your abilities because we did it before. You got this. You can do this. Alrighty, now we're going to talk about the second step, which is the standard error. Well, standard error is kind of fun because if you'll notice, it is sigma hat over the square root of n. Doesn't that look familiar? That should look familiar because sigma hat over the square root of n was in the t equation. Sigma hat over the square root of n. You've already solved for this before, so naturally here we are again. So what that looks like, and I'll go ahead and rewrite this, but you should already know that sigma hat, the equation for that is the square root of SS over n minus 1. You could also write DF right here. You could also write degrees of freedom here, and that would work. I've just limited where we write DF on purpose, just to ease confusion, but you know, you can do what you want. All right, so then what you do is you take this and you plug it back into here, and then you take this value divided by the square root of n, which will give you your SE. So now step 3 is us plugging it all back together. So we got 95% confident that X bar plus or minus, oops, I didn't leave myself enough room, that's okay. Plus or minus T star DF, which is what we solved for up here, times standard error. Boom. So you have both of these pieces because we solved for them. That should make sense. Alrighty, well, I want to go ahead and write what the equation would look like if we have 2 X bar values. So if we have 2 values for X bar that we are going to see what the difference is, we can do it like this. So we got 95% confident that X bar 1 minus X bar 2 plus or minus T star DF times SE. Well, to solve T star DF, you'd go up here. To solve standard error, you'd want to think about that, right? Think about what that means when you have 2 groups. Think about what that equation would look like. But also, let's talk about it. So we're going to have standard error. The equation for standard error when you have 2 groups, right? Remember, 2 groups is sigma hat pooled times 1 over n1, I'm sorry, the square root of 1 over n1 plus 1 over n2. That looks familiar, doesn't it? Should. So this is when we have 2 groups. So sigma hat pooled, remember you never go to the pool by yourself. You always go with a group. Well, this part should be fairly easy to plug in, but remember how we solve for sigma hat pooled is sigma hat pooled equals the square root of SS1 plus SS2 over DF1 plus DF2. So again, like we set up here, you take the value of this, the equation that you solved for here, and you'd plug it back into the standard error equation. Same as up here. So if you want to note to yourself that this right here, sigma hat pooled times the square root of n1 plus 1 over n2, I know I said it wrong, keep moving, is standard error. That right there is standard error. You're using the same equation, the same information to solve for standard error to put in your confidence interval values to solve for confidence intervals. So this is what you do in the case of 2 groups. Think about your T star DF, right? SE is going to be very different. Oh, I forgot a parentheses right there, right? Your X bar 1 minus X bar 2 should be fairly easy to solve for. Remember that whenever you're using X bar 1 and X bar 2, you could potentially assign those groups. Think about if you want it to be positive or negative, etc. Alrighty, we are almost done. We are actually to the last 2 units of the course. Are y'all excited? Alrighty, let's talk about unit 9. Now unit 9, so remember units 5 through 8 were all exam 2. Make sure you go look at your exam 2 and see if you liked your scores, see what you messed up on consistently. Look at the notes that I gave you. I know that they're not very, they're limited, but that's because I want you to go look at it and figure out what you think that you did wrong. Because in these last 2 units, we switched gears quite a bit. So in unit 9, we were all about JASP. Remember, JASP is something you're going to need in your research class, in your capstone course, and I even use it in my PhD program. JASP is a really good friend, right? Don't delete JASP. Don't ghost JASP. Remember JASP. Alrighty, so what I'm going to do is I'm going to walk you through the 7 steps of how to basically use JASP, what we need to do. So this is assuming that you've downloaded your data and you've uploaded into JASP, right? The first thing you're going to do is you're going to look at the data in JASP. So I'm going to put look at data. This just means that you've uploaded your data into JASP. You could also write this as the first step is upload data to JASP. That's fine too. But basically, I want you to make sure that you're going through and you see what your data looks like. You have all these variables, you have all these participants, and here are all their scores. The second thing you're going to want to do is you're going to want to look at variable types. Remember, these are those little boxes at the top that have the drop downs, and you would select the type, right? So it has a little ruler, the Venn diagram, and a little bar chart. You'd want to make sure that you select the correct one. Alrighty, part 3 would be, well, now we want to look, or we want to calculate really, the descriptives. This would mean that you look at the drop, you go to that first little box that says descriptives, right? And you click and you look at maybe the averages of all your participants. You could split by male and female. You could see the different averages, that sort of thing. You want to look at what your descriptives look like. So 4 would be to run the test. Now, remember on the homeworks or on your practice problems that we worked through, I gave you a situation and then I told you to determine what type of test to run. That's how you know what type of test to run. So go back and look at the problem to decide which test to run. Step 5 is that you'd look at your results. Remember, JASP was so nice. All you did was you went through and you picked which test to run. Let's say an independent samples t-test. You plugged your variables in and then you looked at your results. Plugging the variables in is part of running the test. Looking at results is going to help you to do step 6, which is make a decision. If you don't know what it means to make a decision, remember this is with hypothesis testing. And then finally, step 7 is you make a conclusion. So remember when we say run the test, all semester long, what we've been doing is running the test. All semester long, we have been setting up our knowledge of how stats works to run a test, to be able to look at the results that we calculate, to be able to make a decision and draw a conclusion about our data. And we can do this all in one unit. You might be like, well, Ms. Bowman, why didn't we not just use JASP the whole semester? Well, yeah, we could have done that, but would you really understand how the stats work? Would you really understand what we were doing? Would you really understand what a t-score or a z-score is? You're like, Ms. Bowman, I still don't understand. That's fine, but you know how to calculate it, you know how to work it, and that is a big part of understanding what something is. And I'm very proud of you. Good job. All right, so now we're going to go into Unit 10, which is Bayes. Now we're going to get to switch over into Bayesian land. Now, in Bayesian land, I'm just going to give you the notes of what we did and what was important. So this is the last part of the video, so please stay tuned. But the first step we do in Bayes world, but after we read the problem, after we know our parameter estimates, yada, yada, whatever, we're going to calculate a t-score value. So we got x bar minus mu over the square root, over sigma hat divided by the square root of n, So x bar minus mu over sigma hat over the square root of n. We're going to take that sigma hat and we're going to calculate it. So sigma hat is the square root of ss over n minus 1. You know how to do that, right? So then what we do is we take that, so we plug that back in and we get our t value. So that equals t. We would take that t value and we would plug it into the calculator. So step 2 is t equals, plug it into the calculator. Now, cool, we get a printout. We get it a value. And by the way, real quick, when I say Bayes, this is the Bayes calculator. So make sure you look at calc type. Right? We've changed up the calculator type. So don't go back into the old calculator that we used at the beginning. Now we're using the second calculator that's listed on Canvas. So make sure you do that. But cool. So now we already have a printout. We already have if our test is going to be big or not, right? If we're going to have evidence for it or not. So we have this t-score. Well, what does this t-score mean? Well, let's take a moment to talk about further what Bayes is. So I'm going to put note. What we need to know is that BF01 means that we have evidence for the null. So if on this calculator you see BF01, you might have evidence for the null, whereas BF10 is evidence for the alternative, right? The nice thing about Bayesian land is that we can have evidence for the null and or the alternative. P-value world, we don't really have evidence for the null. We just say that there isn't an effect. We don't see an effect, so we're going to assume that there's not one. Whereas in Bayes world, we can have evidence of no effect. That's one of the really cool things about Bayes world. But what we're going to do is we're going to look at what the calculator gives us, what we get out of the calculator, and we're going to think about which one we have evidence for, what that number is. So I'm also going to write down here what the chart is. So if you get a Bayes factor in this that is 1 to 3, values 1 to 3, we're going to say it's weak. This is a chart for BF, chart for Bayes factor. We're going to say it's weak. Now, if we get a number that is between 3 and 10, we're going to say it's moderate. And if we get a value that is 10 plus, we are going to say that it is strong. So whatever this little calculator gives us at the end, we can interpret based on this chart right here. This chart's very helpful. I actually have it right here. Lives in my little office, right? My little chart. But what I want you to remember is that in Bayes world, these are guidelines. These are the researchers interpreting their data, being scientists, right? Looking at their data and giving an estimation or giving an assessment for what they believe it is. So if it's weak, moderate, or strong, they follow these general guidelines. But what the researchers want us to know is that they don't want these to be very strong, right? We don't have to follow this at all times. This is just a guideline, right? It's not a rule, it's a guideline. Anyways, so then what we do is we would think about which one we have evidence for and how strong it is based on the T. So if we get T, if from the calculator, if we get BF10 has 10, right, or BF01 or BF10, 10, that means that we have evidence for the alternative that is strong. So then the last step would be that we would conclude, we would make we would write out what we got. Now I'm going to write out what we wrote out in the class together so that you can remember this. And I'm going to add in like little spaces where you can add in the information from the specific problem. Remember that the statement I'm about to write, you can copy verbatim. So we have assume 1-to-1 prior odds for the alternative and the null, I'm sorry, the null and the alternative, the observed data, updated these odds to, this is where we would write the Bayes factor. If you want another example of this, please go look through your notes. 2, 1. In favor of, right here, I'm just going to write the word hype for whatever hypothesis it has, right? So whichever one of these. So actually, I'm also going to write this pulls out a Bayes factor. So we get the Bayes factor from the calculator and plug it into here. And then we have in favor of which hypothesis, right? It tells us here, but I want you to remember which one. 0, 1 means null and 1, 0 means alternative. This is equivalent to a posterior probability probability of P of blank given the data, oh my gosh, equals blank. So I'm also going to write hype here because this is where you denote which hypothesis it is, right? So the probability of the hypothesis, so the null or the alternative, given the data equals a posterior probability of blank. Now this is probably going to be 0.0 something. This also is going to come from the calculator. That's at the very bottom. And you pick whichever one you're supporting. So your alternative or your null. And so with that being said, that's really the end of our course. That's really the end of what we went through. That's really the main ideas. So in summation, we went from 1 all the way to 10. Please make sure that you're prepping for your final exam. This video is a great way to prepare. Make sure that you understand and can follow the flow of each of these. I'm confident that each of you can. Please remember that I will not give you anything on the exam that I do not think that you are capable of doing or completing or, processing. I believe in all of you, especially if you've been doing the work and following along and watch this video. With that being said, I want to take a moment to say that I really have appreciated all of you being in my course. I hope that you've enjoyed the course too. We're almost done. It's been a long course. We're almost there, but you got this. Please let me know if you have any questions, and I will see y'all later. Bye now.